Okay, I think I'm going to go ahead and get started. All right, so today, the last topic is a little different from the others. I'm going to be talking about some work we've done with aerogels to help clean up air pollution. And this is related to the fact that aerogels are so porous in the surface area. And can you take advantage of that property? And one way is through using catalysts. So just a little bit, I'll talk about automotive pollution and methods for, so mitigating means reducing, I don't know if you know the word, so it means to reduce automotive pollution. Talk about why aerogels, and then I'm going to talk a little bit about the catalytic aerogels we make. I'll focus on copper alumina aerogels. And then at the end, I'll talk a little bit about how you might put an aerogel into a catalytic converter. So background is obviously air pollution from automobiles is not good. So it's a significant source of air pollution. Do people here drive more diesels or more gasoline?
More diesel nowadays.
Yeah, more diesel now, yeah. Yes, diesel is more expensive in the United States.
Really?
Yes. Yeah, so.
Now, because of war, the price of gasoline and diesel is pretty the same.
Okay.
But in the past, the diesel is cheaper.
Yeah. So,
cheaper.
yeah. So most of what I'm talking about will be gasoline engines, but the same idea somewhat applies. You could do the same thing with the diesel. They have also the pollution control stuff. So in the US, and I know similar in Europe, there are regulations about what a car exhaust can have. So there are lots of demands and lots of changes and requirements, and many more. In the United States, we have many more electric vehicles now. I don't know how many, if there's many electric vehicles in.
Not a lot, but
Yeah. So in the US, there are a lot of electric vehicles. Anyways, and then there's new engine cycles, there are new fuels, and all of these things change the characteristics faced by after treatment systems. And so those are, again, after treatment is the thing that cleans up the automotive pollution. A catalytic converter is what's used. So it makes it hard to meet those challenges. So the main pollutants that come from an automotive gasoline engine are carbon monoxide, CO, various oxides of NO, so we might have NO, NO2, and we just call those NOx, NOx, and a bunch of unburned hydrocarbon species, typically in vapor form. We'll call those HCs. So I'm going to refer to how we can remove CO, NOx, and HCs from the exhaust. That's what we're trying to do. And those are the three major pollutants of concern with automotive. You know, when you get the diesel, you have also the problem with particulates. And I'm not going to talk about that, but that's another area where aerogels could potentially help. So carbon monoxide is bad because it displaces the oxygen in your blood. And let's do that. Hydrocarbons and nitrogen oxides react in sunlight and they produce smog, and these are bad for breathing. So if we talk about combustion chemistry, the fuel is represented by a formula, some number of carbons and some number of hydrogens, CXHY. So gasoline is typically C8H18 and diesel C12H23. So when you burn the fuel, if you have complete combustion, it means you have enough oxygen so that all of the C's go to CO2 and all of the H's go to Okay, and that would be fine. Not that CO2 is good for you, but it's not considered a pollutant. It's just a greenhouse gas, and water is fine. But in actuality, what happens is you have incomplete combustion. Okay, so you may not have enough oxygen to completely convert the C's to CO2 and the H's to H2O. So what you're really going to get is some CO2, some H2O, but you're going to get some CO and some HCs. So unburned hydrocarbons and some carbon monoxide, because you don't have complete combustion. And then you get thermal NOx formation at high enough temperature. The nitrogen and the oxygen will react and give you NO and NO2. So we call these different nitrogen oxides, which are not good. And so when you look at an automobile exhaust, okay, this plot here on the bottom plots air-fuel ratio. So it's the ratio of the air to the fuel going into your engine. And then we have this line here, which plots the ppms of NOx as a function of air-fuel ratio. We have this line, which plots ppms of hydrocarbons versus air-fuel ratio. And we have this line here, which plots its percent of CO as a function of, and it's plotted over here, as a function of air-fuel ratio. So fuel rich is over here, and it means there's more fuel and less air, which is where you get more power. Okay, powerful, but you get incomplete combustion. So you get kind of your best power at an air-fuel ratio of about 12.5. But you have, if you look at that, you have relatively high levels of HCs and very high CO, right? Process here. Relatively low NOx under those conditions. So fuel lean means there's less fuel, and that's over this way, less fuel and more air, which results in more complete combustion but less power. So over here on this side, your best economy is at about 16 air fuel, and you're low on your HCs, so as low as you can get. You're very low on your COs, which is great, but you're terrible on your NO. Okay. So stoichiometric is the air-fuel ratio where you have just the right amount of oxygen to completely combust your fuel. And so typically, engines are designed to operate around this point. They don't operate at one, they dither. They go fuel rich, fuel lean, fuel rich, fuel lean, something, like that. Because here you do pretty well on CO and HCs, not great on NO, but if you go a little bit rich, you can cut down on your NO. That's what they do. So the device that we use in gasoline is called a catalytic converter, which Google says is a catalysator, but that means catalyst. Would you call this thing a catalysator? No, what would you call that? On the thing under your car.
I don't know what really is it.
It's the thing like it's pollution control. Maybe, okay. So the industry standard for gasoline engines is we call it a catalytic converter or a three-way catalyst. So catalyst is something that promotes a reaction, right? And it's three-way because it has to do something about this carbon monoxide, the hydrocarbons, and the nitrogen oxides. So that's why we call it, and I will be talking about, I never moved this on the first try. Come on. And then I let go. Oh, yeah. All right, there we go. Okay. So there are three reactions that a catalytic converter is designed to promote, but so here's an actual picture of a catalytic converter. Here's a picture of a car, and the catalytic converter is underneath. Here's your engine, and it's on the tailpipe where your exhaust goes out. We call it the tailpipe, and then at the end is where everything comes out. So catalytic converter consists of corderite or honeycomb support. So this in here, blown up here, is a ceramic material with channels going through it, little channels that the gas can flow through. And so you have coming out of your engine, you have the NOx, the CO, and the hydrocarbons flowing out, amongst other things. And they flow through this, and this channel is coated with aluminum oxide wash coat, it's called, and it's impregnated with metal catalysts. So the metal promotes these reactions that convert the pollutants to nitrogen, water, and CO2. And that is the goal of a catalytic converter. And these are the reactions that occur, and they are there are two oxidizing reactions where an oxygen is added. They call that oxidizing. So 2 COs plus an O2 will give me 2 CO2. My fuel, depending on what my fuel is, reacting with an oxygen will give me CO2 and H2O. Okay, so this is an HC. So these reactions like to occur in an oxidating environment, which means there's lots of oxygen around. The third reaction is to convert the NOs to O2 and N2. And that's a reducing reaction because you're taking away an oxygen. This reaction doesn't like to happen when there's a lot of oxygen in the exhaust. So that's why you sort of vary your engine around this ratio to create conditions where there's less oxygen and where there's more oxygen, so that you can promote these reactions. And so these catalytic converters, the material that they use on them is our precious group metals, PGMs, that's what I'll call them. So to work well, a three-way catalyst uses a combination of platinum, palladium, and rhodium. So the metal that's on these surfaces is that material. In nanoparticles, they distributed it in something else. It's not solid platinum, things like that. They often also have a component such as ceria. Ceria has the ability to store oxygen and then release it. And it's all wash coated, is the phrasing, wash coated with a slurry, which is a mix of alumina onto the substrate. And so, here's showing in red the polluting gases. And then here's the substrate, which creates a reaction. And now we have the blue, which is the better stuff coming out. And so there are many, many formulations and configurations. And by that, I mean how much platinum, how much palladium, and how much rhodium do you use in your setup. And sometimes they're designed in two parts. One will have more of one, and the other more. One might have more palladium, the other more rhodium. So it's very challenging for the automotive industry to keep up with designing these. Some of the biggest challenges are that, I should have had a plot. Platinum, palladium, and rhodium are very expensive. So they're really expensive metals. In addition, they have a very high environmental impact due to mining, the way they're mined. Their supply is uncertain because of geopolitics in the countries where you can find these materials. So it's there's a lot of work that goes into recycling them as much as I can, but the automotive industry would love to get away from using platinum group metals in their catalytic converters. And that's sort of where we are. And then, so you often see, this is from Palermo today, so I don't know, it's like last month, you often see stories about thieves stealing these things. So they cut it off. It was here, they cut it off because the metals are valuable. And so you always see these. I see them, it's all stories. And so I looked online, found one from Italy. So there's a lot of research aimed at either minimizing how much of the PGMs you use, as well as maximizing the activity. So that means more active, that they catalyze better. So just does a better job. Minimizing the light-off temperature. So the way that you characterize a catalytic converter is by defining a light-off temperature, which in this case is defined as the temperature at which 50% of the pollutants are converted. So if I started out with 100 COs, whatever temperature I'm down to 50 COs, that's called my light-off temperature. So it means your reaction is taking place. And then also increasing the longevity of any PGMs that are used. Other issues with the catalytic converter are that between 60 and 80% of the hydrocarbon emission is usually emitted during the first 2 minutes. So when you start the car, the catalytic converter is cold, it's a cold start, and it doesn't act efficiently. So the pollutants just go through, you're not converting anything. So in order to meet low emission or ultra low emission standards, it's necessary to try to reduce that light-off temperature or the time required to reach light-off, or both. If we can reduce it, if this thing heats up within 30 seconds, that's great. Or if instead of having to reach 200 degrees C, we started converting at 100 degrees C, that would be better. So either of these. So you want a material that's stable at high temperatures, because if you have something stable at high temperatures, you could conceivably, so here's my engine and here's my catalytic converter. If we could move it closer to the engine, because if it can take high temperature, that would be good. So something that's stable at high temperature would allow you to position the three-way catalyst closer. And then if it's closer, it's going to heat up faster. And the other thing is, if we could make materials with low thermal inertia, or low mass, they don't weigh much, they'll heat up faster. So that's another thing where new materials could help out. And so we've learned about aerogels. So I've just talked about things that are true of aerogels. So why aerogels? And this actually started, we've been working in this area for about 13 years. I think I showed students, says, can I do this? So this particular student said, his idea was, could I use aerogels in a somehow in a catalytic converter? He started off, he came up with a way to make, this is an alumina aerogel. So why was this even something worth pursuing? What is it about aerogels? Well, thermal stability, we know they're stable at pretty high temperatures. So that being stable means you could reduce when you impregnate the material with the air, with whatever catalyst, whatever metal, when it gets hot, it sinters, and so the particles agglomerate. So if I have a bunch of nanoparticles, suddenly they become bigger particles with temperature, and that's not necessarily good. So these were our hypotheses that aerogels would help with that. And then again, because they could take a high temperature, we could put a catalytic converter made from aerogel close to an engine, and that would reduce time to light off. Same thing with the low thermal inertia. The material can heat up fast, and that could reduce light off. Aerogels have very high surface area, so that has the potential to result in more active catalytic sites and improve gas-solid interaction. So because you have this porous material with lots of surface area, you could have lots of metal particles that will participate in the catalysis. And so this is why, in fact, we're studying gas flow through aerogels, because we're interested in understanding what we can get. And then finally, with the aerogels, we're able to tailor the chemistry. You can do a lot of things with it. It's the sol gel process. You can do a lot of things with that to make different types of aerogels and do different things with them. So that sort of was these were our hypotheses about why you would want to use aerogels in a catalytic converter. People have been doing catalysis with aerogels for years. That's not new. People have been studying the use of them to catalyze different reactions. What was new is that nobody had tried it to use an aerogel to do three things, to do these three reactions. So aerogels as a three-way catalyst. We were the first to do that. So, okay, so I'm going to talk a little now. So that's kind of the background. Any questions on kind of the background and why we're doing that? Okay, so now I'm going to talk about how we prepare. Two things: how do we prepare, and how do we characterize those aerosols? Like, what do we have to measure about them to tell that they're any good? So we have been able to make catalytic aerosols using our process, a number of different ones. We've made vanadium silica, this yellow, which is used in a photocatalytic application, as well as titanium silica. Silica, most of what I talked about previously is all silica. Silica is not a particularly catalytic material. It's fairly inert. So we switched then to doing things with alumina. So this picture is an alumina aerogel. And we switched over to doing some work with alumina, but alumina itself is not enough. So we dope the alumina with nickel, cobalt, copper. These are the ones that we've been working on. We've also done ceria and chromia. And then we've also go back to silica. We did something with silica with adding copper nanoparticles. So these are some examples of the type we can make. These two are monoliths, solid pieces. But for catalysis, you don't need that. So we don't typically. These pieces are what we need for doing catalysis. So most of what I'm going to talk about are best performing non-PGM material is the copper alumina. So I'll talk about some of the work we've done with that. So to make it, and Professor Carroll probably showed this slide or something like it, you start with a salt that contains aluminum, aluminum chloride in ethanol, and you stir in propylene oxide, which is a catalyst, and you combine all of that, and in about 3 minutes, you formed a wet gel. So it's like a sol gel. Again, this is the thing. And we could take that and rapid supercritically extract that to get something like that, which we've done. But because we want some copper in there, And so our most success, we could either add the copper when we do this, is one way, called the co-precursor method. But we've had a little more success doing an impregnation method. So we let this sit and age for about 24 hours, and then we break it into pieces. So it's going to be broken, it's going to be wet, but it'll be pieces like this. And then we soak it, or we put it in ethanol that has a copper salt in it. So it goes in and it sits there for 24 hours, and the copper gets into or penetrates into the aluminum gel. And so we have a wet gel with copper in it. Okay. And we have to do some solvent exchanges along the way. So it's like this is not a fast process, not like the extraction is fast, but preparing the aerogels is not fast. You have to do these steps. But now I have a wet gel made of alumina with some copper in it. And I take that and I put it in a mold and let something like this. I break it, it's broken into pieces. Again, it's not a solid piece, it's little pieces. And I do rapid supercritical extraction. That step's fast. That's just a 4-hour process. But the rest of it takes like 4 or 5 days to do. And then when I'm done, I get some copper alumina aerogel pieces. And so this is realistic. It looks blue when you make the wet stuff. Oh, that one's green. I think that might be heat treated. And it comes out kind of reddish when we first make it. So copper is an interesting chemical because it has many different forms of copper, and they have many different colors. And we see that in our aerogels. So that's just quickly how we make them. And then we do a lot of characterization methods, and I've talked about all of these, but I haven't talked about this one, so I'll talk about how we do the catalytic testing. But so we do scanning electron microscopy, and that gives us topographical information about the aerogel. And we do energy dispersive X-ray spectroscopy, EDX, and I've showed you images of these things. And that just tells us what's in the aerogel. So if we make a copper alumina aerogel, we need to look at it and see is the copper in it. And so we use that kind of characterization. We also do powder X-ray diffraction, which I have not talked about. X-ray diffraction just uses X-rays to probe a material and tell us about crystalline phases. And so I'll show some of those results. And again, we do the same thing there. We're going to be able to tell something, between this and this, we can tell something about the form of what's in that aerogel. And we do gas adsorption, which I've talked about, that provides information on the surface area and the pore distributions, which are of interest. And then we have, so we call it UCAT, Union Catalytic Aerogel Test Bed, just testing system. And that's what we use to provide information about how effective the material it is at catalyzing these reactions. Remember, we're trying to make these reactions occur. And we do that by measuring sort of how much CO goes in and how much comes out. And so that was actually a fun project. This is a schematic of it. Took about it's an in-house built thing, took about 3 years and about 10 students to build, something like that. Because you can either purchase equipment that costs millions of dollars, or you can build your own. So we built our own. So the system looks something like this, schematically. It consists of a gas control system. So, and I'll talk about the blend, but we are mixing our own gases to have a certain amount of hydrocarbons, a certain amount of CO, and a certain amount of NOx in it, because we want to simulate what comes out of the car. The other way to do this is to have a car in your lab and run a car, and then you can do sort of the same thing. But we make our own. We can't fit a car in our lab. And we have a gas control system that says how much of the gas to run. We have separate bottles. This core blend has nitrogen oxide, carbon dioxide, some CO2, HCs, but no oxygen. And the rest is N2, because if we have the oxygen in there, reactions are going to occur. So we keep that separate, and we mix oxygen in afterwards. So the core blend and air are metered by this system, and they're sent through to an oven. Okay, and the oven has 2 test sections. So you can put some aerogel in here and some aerogel in here. And there's 2 just because it's faster to do 2 at a time. And we have the room. And we also have in the line, we have the ability to humidify the gas, because an automotive engine has water in it. What comes out automotive exhaust has water. And so we can humidify. That's a newer thing we've been doing. And then we have gas analyzers. So there's 1 gas analyzer on each test section, and they can be hooked up to a bypass, which measures the amount of the pollutants in the mix. So we know what's going in. And then they can be hooked up on the outside, and we can then say what's coming out. So we have 2, we have 2, 1 for each side, and they are connected either to the inlet or the outlet. And then the oven here is used to set the temperature. So we run temperature sweeps from, I don't think we started, we could do 50, but we usually start at about 100 degrees C. And then we go to 150, 200, 250. And we go through each set of temperatures, and we measure for each one what the conversion is. So this is what it looks like in practice. So again, here's the oven. Here's what that test section looks like in there. It's a cylindrical thing. We can put one more image. And this is the oven controller. This is a 5 gas analyzer. We have 2 of them. They look like this. They're used, I don't know, in the United States, you have to go and get your emission systems checked. You go to a garage, to a gas station, and they check that your car is performing like it should. Not in all states, some states. Do you do that in Italy? Do you have to get your car emissions tested?
No.
No, okay. Yeah, I don't think in New York we don't have to do it. In California, when I lived there, you had to. California is probably where that picture was taken with all the pollution. But anyways, this is what they use. So we have that sort of same thing. We have our bottles of gas over here. These are all the meters, excuse me, to control the flow, and this is the interface. So that's what that looks like. This picture, I think, was taken when we only had 1 section. So now we have 2. So it's pretty easy to use. Lower cost than what's out there. It takes us about a day to analyze 1 sample. So we'll start in the morning and we'll run all day, and we'll get the results at the end of the day. So some of the things, what we care about. So here's kind of just a schematic of the oven. Right, here's the flow coming in. There's a sort of heat exchanger there to make sure the gases get hot. Here's the test section where the sample goes. And so we measure the temperature here and here, and actually we measure inside the sample too. This is an oven, so all of this is heating that up. And so we flow through, and the things that we care about when we run tests are, what is the gas blend? We use propane and propene, 2 different hydrocarbons, in a certain mix, and I'll talk about the gas blend in a minute. So space velocity is related to how long it takes for the gas to flow through the test section, right? Just the flow rate. We use 1/seconds. It's sort of an industry standard. We test these materials. We typically start at 200, maybe a little bit lower, and go up to about 650 degrees. Before we heat a sample, we have to preheat it. So when we just make it, before we test it, we heat it to 800 because it changes, and it will change when we do the testing. So we preheat it ahead of time. We use about 20 milliliters a sample, and we can do separate tests. So one of the things we do is we test with and without extra oxygen in there to mimic fuel-rich, fuel-lean. We have the ability to do that on like a 1 hertz where you can switch between it. We haven't done it yet, so we do them separate. We do a test with extra oxygen or with regular oxygen each time. So we change that. You'll see some of my results. So the gas blend that you use is important. We started with a simple blend called Bar 97. I don't even know what that means, but you could buy it, and you could buy it in these little tanks. And it's sort of simulating, it's what gas stations used to calibrate these things. So it had a specific blend with a specific amount of hydrocarbons, CO, NO in it. So we used that for a while because it could be purchased. But then when we started doing a lot more testing, we decided to mix our own, to develop our own system and mix it. And so we use what is a simple blend. Sorry, we use what is recommended. There's an organization in the US that recommends anybody who does testing with catalytic converters use specific amounts of hydrocarbons, nitrogen oxide, carbon monoxide, H2, CO2, water, and oxygen. And so they specify that amount. So your HCs are in the ppms, and so are your NO, very small quantities. These are not good gases to work with, so we have to be very careful. All this is done in a hood. So they recommend a mix of gases, ethene, propene, and propane. We do not have the ability to differentiate between these, so we just use propene in ours. So we get an amount of propene in there. And these are the different cases. So we run, these are our gases. They're as similar to this as we can. We use this as a guiding principle. We're not exactly there. And we run different cases. We run high O2. So you can see here, 1.15% O2 versus low O2, 0.12. So there's a difference in the amount of O2. So this would be like a lean and a rich case is what it's simulating. We run cases dry. So there's no water added, no humidity. That was here where we add water. So we do dry testing and we do humid testing. And then we add 13% of the mix is steam. It's not liquid water. It's in gas form. And so the reason we did this in the beginning, and the initial results I'll show you are dry. We didn't know how aerogels were going to react. Well, we didn't have the ability to do it, so we had to add that. And then we needed to know how the aerogels would react with the water because the water destroys aerogels. Okay. Just trying to think would be good for a break. Let's go a few more minutes and then we'll take a break. So what I'm going to do now, so I've told you about some of the combustion chemistry, pollution things in cars, why we care. I told you how we make the aerogels, told you how we characterize them, and explain the catalytic testing thing, because that was sort of the most important. So now I'm going to take you through some results that we had for copper alumina aerogels. So these were some initial studies we did, and we didn't exactly, one of the problems when you have the wet gel and you put it in a solution containing copper, you don't know how much copper goes into the gel. So we looked at an experiment with what we called high and low. We put a lot of copper. You know, the ethanol in one case had a lot of copper, in the other case less copper. So we called it high-low. And we did it with alumina, and we did it with silica. And these colors are like crazy looking colors. This is how it looks when it's just processed. And when there's a lower amount of copper, it looks a little lighter, almost white. Yeah, so you don't see as much. And then when you put it in silica, it looks brown. So it's very strange. So these are the first studies we did. And so we did some SEM imaging. And this bar is 200 nanometers. So these are in very close. And we see these specks, these little, right, looks like little particles in there, probably on the order of 10 or 20 nanometers. So we thought they were copper, but you can't tell just from SEM what it is. Doesn't tell you, just look at the surface. But using this energy dispersive X-ray imaging, which is built into the SEM, we can tell what things are. So we focused in on one of those particles here, and this is sort of the SEM image. The scale on these, this is 200 nanometers also. So we focused in on that, and then we looked at, is there any copper there? And sure enough, that spot is bright red. So this is the copper image showing you copper. There's copper also in the backbone, but here it's clearly copper. And if you look at alumina, everything else is alumina, and there's less alumina there. So that tells us that we were, you know, we didn't have any idea what we were getting, and we found we were forming these nanoparticles in the material. So that was good, just finding that out. And so then we did X-ray diffraction. And so X-ray diffraction gives you information about the crystalline form of things. And so basically you get a pattern that on this axis is intensity of a signal. And this is the angle that you have a sample and your X-rays are moving around different angles. And so where you get peaks is related to different crystalline structures. And the same crystalline structure can have a peak, you know, 5 or 100 structures could have a peak here, but it's the pattern of peaks having a peak here. So for example, this peak, and this peak are are signatures of boehmite, which is a form of alumina. So by identifying, and the intensity is important. Boehmite has the highest peak at this angle. You know, the next highest here, the next highest here, and it probably has 4 or 5 more that we can't pick up. So it allows you to identify that. And then we also saw copper oxide, CuO, and these peaks are related to copper oxide. So this bottom trace here is the as prepared sample. That's the one, that is this stuff. We hadn't done anything to it yet. When we heat it to 800 and we run tests and we do an X-ray diffraction pattern again, it changes and it looks like this. And now we do not have these peaks anymore. They're gone. But instead, we have these peaks that correspond to gamma alumina, a different form of, it's just a different form. The alumina transitions as you heat it up. And gamma alumina is good because it's a little more reactive for us. There's other forms of alumina. If we go to higher and higher temperatures, the other forms of alumina will come out, and they're not as good. So we're happy to see gamma. And then we see more peaks related to copper oxide in there. So anyways, what this tells us, it's hard to do X-ray diffraction because we have very little amount of the metal in there. The aerogel itself is amorphous. Much of it is amorphous, so you can't see, especially the silica. But we are able to pick up some of these peaks. It's hard to do, but you can get them. And then we looked at heat treating these materials. So these are the different colors. So if we go like from a red to redder to kind of green. So this means that we put it in an oven. Left it in the oven for hours, and I don't recall exactly how many, at 100 degrees C, and took it out and looked at it. Did the same thing at 200 degrees C. These are all different samples, but they go through all of these odd, so 1, 2, 3, 4, 5, 6, 7, 800 degrees C. They go through these weird color changes as we do this. And we did the same with the silica. They also go through some weird color changes. This is copper changing its form that it's in. And we did look at surface area versus temperature. And these materials, so the copper silica starts off really high surface area and it stays relatively high, above 600. The alumina starts off at about 400 meters squared per gram. And once you heat it above 400, it goes way down, like 60, which takes away a little bit of the advantage of, wow, it's high surface area. But this is a much higher surface area than the catalysts they use now, which tend to have 2 meters squared per gram or something like that. So we've lost the high surface area when we heat it. Not so much with the silica, but the silica is not quite as reactive as the alumina from a catalyst point of view. Okay, I ended with this. And so I said initially, sorry, I'm not going to do this every time. I'm trying to just move it. I know, but I go and then I do this. It will move though the next time.
Okay,
see?
Every time.
Okay, so we didn't know how much copper we were getting in there. I told you that, and we needed to figure that out. So we came up with a way to do that by looking at an indirect way. We used a spectrophotometer we started with copper in, I think it was in ethanol. And we put our wet gel in there and some of the copper went into the wet gel. And then we still had this ethanol left over with still some copper in it. So we used a spectrophotometer to determine how much copper stayed in the solvent and didn't go into the aerogel or the wet gel. And we were able to do that by mixing up concentrations of copper, of known concentrations of copper in ethanol, and measuring its spectroscopic at a certain wavelength. We could calibrate, come up with a line that says, you know, if the intensity is 20, you have 2 grams of copper. If it's 40, you have 4 grams of copper, something like that. So we were able to do that. It gives us a little better idea of how much copper is in the wet gel. Doesn't tell us how much is in the aerogel, because when we supercritically extract, we could lose some. We don't know. And it's not like we can weigh. It's so little copper, we can't exactly tell how much we have. So, but we did do these studies. So the first thing is how much copper is in the aerogel, and how much copper can we put into the aerogel, and how good is that for converting the pollutants. So we'd start out, this just means there was 2 grams of copper in the initial salt, 4 grams, 5 grams, etc. And so we were able to figure out when we made these, how much, and the numbers are the number, we did a lot of samples, how much copper went into the gel, okay? And how much was lost, or how much we started with the salt and how much went into the gel. So we were able to figure out kind of how much copper we had. So when we used this recipe, we ended up with about 0.48 grams of copper in the gel. That's where we had 2 grams in the solution, about half of a gram went in. When we did the 4 gram, we had about 0.7 grams. And when we did the 8 grams, we ended up with about 1 gram in the solution. So this gave us a little bit of a sense, because we didn't know, we have 2, 4, 8. Does that mean 4 is twice 2, 8 is twice 4? It doesn't exactly, and you can see that it doesn't exactly double. So we were able to figure out how much we put in, so that was good. And then we wanted to say, how much do we need to convert the pollutants? And so we did some SEM and EDX, and that is wrong. That is the 2. Well, I'm not going to fix it. So we looked at the SEM images of the 8, the 4, and the 2. And it's gonna bug me. I'm going to change it right now. Sorry, not a mistake. There's 2. Okay. Okay, now I messed myself up. Let's go back. Computer definitely works better when it's not been turned off. All right, now, try now. Okay, so we took pictures, SEM images. These are 2 microns. These are not as close in. And with the 8 and the 4, we would see particles. You can see, a little hard, but you can see those little dots all throughout. We would see them at a lot of locations. And for the 2, we didn't see as many. You know, we saw some, but then nothing here, nothing here. And we look at different locations and we just didn't see as many. So, which makes sense. There's less of it. And we took EDX images, and I actually showed them earlier on an earlier day, that I showed you a picture. It had these beautiful, looked like copper particles in there. So we knew they were copper. So we were able to do that. Okay, but the important thing is this. Here we go. Do it right the first time. Oh, maybe I think I have to grab it at the top. That's what I wasn't doing before. Okay. Okay, so this is an example of the catalytic test bed, the test we do in UCAT. These are tests, these are dry. The test I'm showing here is dry, so no humidity, oxidizing, so a little more oxygen in the mix that we're going. And that typically would be advantageous for conversion of CO and HC. So this plots percent conversion of the CO, 100%, it's all gone. So we measure what's going in, what's going out, what's coming out, there's nothing, you know. 0%, none of it's gone, it's all coming out, versus temperature, okay? So, and the different colors, so this is the 8, the 4, and the 2, okay? And light off temperature, if we drew a line here at 50%, you know, would be around 200, what did I say, 225 to 250 for these, and more like 350 for the 2. So basically what we saw was pretty big difference between the conversion of the 2 and the 4 and the 8. The scatter in the data, you know, these are pretty much the same, the 4 and the 8. Maybe the 8's a little bit different. 8 might be a little better, but not a lot better. Not in the way that 4 is so much better than 2. So this is showing us that, oh, okay, adding more than 2 was good, adding 4 was good, 8 was marginally better. You know, going to 16 probably isn't going to help isn't really going to help. But what's nice is you see we do a pretty good job with these materials of converting the CO at low temperatures. I should tell you the goal is to get below 200. Well, we're not that far. So these are not optimized, or these are just, we made them and tried them. So that was good. This is now the hydrocarbons, dry oxidizing it. They're not converted as well. We do really well with CO, but not as well with the hydrocarbons, right? Not till much higher temperatures. See the same thing? The 4 and the 8 are a little better than the 2, quite a bit better than the 2, although something odd was going on there. Again, you want to get to 50% conversion at as low a temperature as possible, and then you want to reach 100% conversion too. But the 50% is what's used for light off. So that was okay. The next one is the NO. So if I test the NO in an oxidizing condition, it does nothing. It won't go away because there's too much oxygen around. And this is why they do fuel lean, fuel rich, fuel lean, fuel rich. Because if you have a reducing condition where there's not very much oxygen, then you can convert the NO. And so this is the NO conversion versus temperature again, and we're looking for the 50%. And the light off temperature decreases significantly when I go from 2 to 4, right? From 400 to 3 something. So, I mean, these are okay results. The CO results are really promising. The other ones aren't as promising. These tests, I'm trying to think of what these ones are done. The gas we used here was a little different. So then, okay. No, this was a good guess. Never mind. Okay, so that was promising. We're happy. We haven't really done anything to optimize. We showed the effect of how much copper you get in there. So then another thing we did, and we've tested many types of, I have a summary thing at the end of different types of aerogels. I just wanted to show that as an example. That was one of our better ones. So then the problem becomes, how do you turn this into something that can go in this, right, around this. So, because aerogels are fragile, how are you going to do that? So we worked a little bit on that. So the initial performance was promising, but there are a bunch of open questions, primarily because their reputation is fragile and water is known to not be good for them. And so we had to figure out a couple things. It's important to know whether these materials can survive exposure to humid exhaust, so we wanted to add water. And we have to figure out what form should they go in to be part of a catalytic converter. And so we had some ideas. Option 1 was, what if this is the it's called cordierite. It's a ceramic. It's the structure that goes inside a catalytic converter. It's that structure you saw. And you build it, it's like a porous structure, and you coat it with your catalytic material. And so we had the idea, well, what if we go in, yeah, you can't fill the whole thing because then you wouldn't get any flow. Well, you could if we could get good flow through aerogel, but we're not, the flow coming out of your car is too much to go through. But can we coat it? The idea is, can you get aerogel to stick right around the surface? And so, and it's porous, so can you get the aerogel just on the surface? You don't need to fill it, just like a layer. And so we did do that, and we had some luck with doing that, where you could, so this is during the rapid supercritical extraction process. We cut up a piece of this, and we put it in our mold with the aerogel solution, and we processed it. And so we had some luck with that. We did get some aerogel material in there. And we haven't given up on this. We think this has some potential, except that it's not exactly, be a little hard to put a big piece of cordierite in to do in that part of the process. Another option, and they used to have catalytic converters had beads in them, spheres of alumina, and they coat those with platinum group metals, the different metals. So we thought, could we do that with copper alumina? And we can. We process, so you can see there's some alumina beads in here. This is a copper alumina aerogel. We did RSC processing all of it in there. Here are the beads, and here's a picture, an EDX picture of a bead showing you that sure enough, we coated it with copper, so we could do that way too. A crazy way, so I had a crazy imaginative student that thought, what if the aerogel was the structure itself? And you can do things to aerogels to strengthen them, which I've talked about. They don't have to be, these are transparent, you can do anything you want, you strengthen them. And so, and building on the laser cutting things that we did, could you cut channels through a piece of aerogel like this? So he laser cut channels in an aerogel, and and here's another one. You can see the top where you cut a pattern through. So if you had a catalytic aerogel and you cut a pattern through it, could that be your catalytic converter? And he was able to test and show that it did some conversion. It wasn't perfect. It was just an initial trial, but it was another idea. So we're just trying to come up with ideas. But in the end, we decided that the most compatible approach would be to do it using the industry standard way, which is, it's called a wash coating process. I don't exactly know how they do it. I think they take the big, that visited car company or catalytic, they won't show you, they won't let you near it. So we visited one place. When we left, you have to go through a metal detector to make sure you're not stealing their platinum and palladium. I kid you not. We had to, like, on the way out, we had to be tested. It was crazy. Anyways, it was one of the big coating companies. Anyways, what they do is they take the big quarterite, the model, that big piece, the structure, and they dip coat it in a slurry that has alumina, their platinum group metals. They probably do multiple processes. They probably dip it, and then they dip it in something else, and then they heat treat it, and they do a lot. But the basis of the method is to make a slurry of the material, which means you have to get it wet. So a slurry, a slurry, it's really, we made a slurry, aerogel and a little bit, a pH 4 water. We had to mix them together. And this actually came about because we were visiting these companies that do this, and we're talking about aerogels, and they said, can an aerogel be slurried? We're like, I don't know. We went home, we went and tried it. We want to see. It makes more sense if you could get aerogel into like a solution that you just dip into. That might be the best way to do it. So we didn't know if we could do it. So we tried. We took some aerogel samples. They were first heat treated. Again, we do this to all the samples at 800 degrees C for like 20 to, I think that's just, I'm not moving that thing. It's 20 to 24 hours usually. And they were slurried by taking 10 milliliters of the heat treated aerogel and mixing it with an acidic solution from nitric acid and deionized water. And so we simply poured the aerogel, this stuff. We crushed it up first, and then we added it into the water. It's hard to get it to mix, but we stirred it and heated it for like an hour and a half. And then we took the top off and heated it even higher to drive off all the water, to let it dry out, basically. So we added it, and then we let it dry it out, and it looked like this afterwards. Right, so it survived. We think, you know, whatever, the proof is whether it's still active. So we studied the morphology using gas absorption, and I think I showed this part, but no, I didn't show this one. So this is, again, pore volume versus pore width. These are the materials as prepared. These are not silica. Silica has a peak down here. These are copper alumina. They have a wide peak, and they peak about 40 nanometers. And they have a surface area of about 300 and 36 meters squared per gram as prepared. When you heat treat them, look at this down here, nothing. On this scale, there's nothing. You don't see any peaks. The surface area drops to 65, which is not unusual whenever we heat treat any of our materials to that high temperature, except for the silica. The surface area drops. But you can see this initial one had a pore volume of 3.5 centimeters cubed per gram. Heat treated went down to 0.12. So heat treating just, it all densifies. It gets, you know, the pores collapse and everything. It's still an aerosol though, it still works. But then the weird thing, you know, so heat treating also the density increases. And then when we slurried it, we put it in the water and dried it out again. The density was still much higher. The surface area was about the same. Didn't compared to how it started, didn't change. But we saw this bizarre thing where suddenly we got some pore volume back. And we don't know why. We just published this and the reviewers were like, why? And we're like, we don't know. we don't know. It's odd. We repeated this several times, so it wasn't a fluke. For some reason, after it's been in the water and it dries out again, you get some of the pore volume. So first thing is it survived the slurrying. Okay, no worse off. So in terms of surface area, similar to just heat treated and better in terms of pore volume. So that was the first step. We did some of this, again, here's an X-ray diffraction pattern where it's intensity versus that angle, right? And those peaks are related to certain structures in there. And so the blue is as prepared. And then as soon as we heat treat, we get these structures, and some of them are related to the gamma alumina. And others indicated that we had a copper alumina oxygen spinel, it's called. It's a chemical structure that was in the heat treated material. This is meant to show it's in the heat treated material, it's in the slurried material, and it's in the material after we test it. So no big changes, except we always see this little bump after we test it. Sorry, these little things that aren't here, which we think has to do with the environment in which we test this. We see it for almost all of the copper materials. But anyways, there's no difference between the heat treated and the slurried. But the big thing was the catalytic performance results. So this is, again, so if we look at conversion of carbon monoxide versus temperature, the red is the regular stuff like I showed you before, and the blue is the slurried. So very, again, within our uncertainty, they're basically the same. We saw pretty much the same thing, and it's down here. We went from 250, sorry, CO from 220 light off to 220 light off, didn't change. Hydrocarbons was similar, maybe a little bit higher with the slurried. So these numbers represent light off. NOx was, the slurry was worse. Here's the case non-slurried. There's slurried, the material afterwards, and with the big degradation in performance there that we see. We don't know why. Again, CO has always been our best thing with the for the copper alumina, but also shown here, just to put this in perspective, the green, we bought a catalytic converter from a car place, and we tested it in our system, and you can see it has light off temperatures, you know, below 200. It's much better than this is where we want to be. This is where we are here. We're pretty good here. We're pretty close here to being, but this thing, we don't know what's in it. It has PGMs. So the idea is to make something that performs as well as a system with the platinum group metals without the platinum group metals. So we're trying to get there. Not quite there. There are other issues with using copper too. So this is like a summary of where we are. This is light off temperature versus all of the different types of aerogels we've made. And so I should say the initial gas we used had a hydrocarbon that was hard to convert, and the clearest hydrocarbon is better. So we see a difference when we went to the recommended thing. And so again, low is better. So the blue is the hydrocarbons, the orange is the CO, and the gray is the nitrogen. So here's some of the early stuff with the copper silica. It didn't do particularly well. This is ceria silica, also not that great. Nickel alumina, cobalt alumina, ceria alumina, copper alumina. So we got pretty good with that copper alumina. And then when we went to the other gas, which is, again, a little easier to break apart the hydrocarbon, we got even better performance. And so here's a chromium alumina aerogel, not too bad. Here's our copper alumina slurry. Here's our copper alumina regular. I believe these are all dry tested. We also did some testing in humid environment, and there are some changes. And then this is what we have finally given into is the other thought about our aerogels is could you put precious group metals in them, but much less than they currently use. So we started doing some work with rhodium, palladium, alumina aerogels. And we're getting very good conversion rates. We're almost at 200. We've vastly so, I mean, you're looking at, we were up here for light off on NO, and now we're down here. So that has really helped. And so we're currently looking at how much of the PGMs do we need to be able to do this? And can we use less in an aerogel than you would in a standard way? Okay, so just open questions and future work in this area. These are research. This is just a research project, and if it was ever going to make it into a car, long-term age is important. How long will they last? They have to do that. We've done several cycles of survivability. We see good short-term survivability. Like we can test these in dry conditions, humid conditions. After it's been tested humid, we go back to dry, we see the same performance. But we haven't done thousands of cycles. We've done 5 cycles, something like that. How would they withstand vibration and physical loading? Poisoning is a problem, depending on what's in the gasoline. If there's sulfur in there, it can poison the copper and deactivate the catalyst. It's a problem with all of the catalysts. Benefits. So survivability is then benefits. We've done a little bit to look at. We talked about increased thermal stability. Does it really help with decreasing sintering? Does it increase lifetime? Does the increased surface area lead to reduced metal usage? And that's the thing we're doing now with the PGMs. And then can the lower thermal inertia of aerogels be translated into reduced light-off delays? And we've done some initial numerical studies on that, trying to show what kind of effect it would have if your whole catalytic converter was lighter. And then in terms of cost, right, the other way of getting around this, if we have to use PGMs are really good at catalyzing these things. That's why they're used. So this other approach we're trying is, can we get away with less of it? And that would be a way to save. And then, are there lower cost aerogel manufacturing techniques? So that's the other thing with that. Okay, do you have any questions? I haven't even asked you any questions. Okay, all right. So that's kind of summarizes it. That's all I have. This is just I wanted to do acknowledgments for, all of the stuff that I presented. At least the research presented of ours was funded primarily through the United States National Science Foundation. And then Union College has a small faculty and student research funds. And so students who work with us get that. And so the catalytic aerogels have been funded by a number of different projects. This is partnerships for innovation. I did do the innovation core with the catalytic aerogels too. We had that. we had a grant to make the catalytic test bed and a bunch of research funding on that. The aerogel windows projects have all been funded through more of the in the United States, it's small business technology transfer funding. It's more for companies and universities to work together. So it's a little different program. So a lot of that's been funded through that, as well as to the New York State Energy Research and Development Authority. And then my colleagues, this work I do with Mary Carroll and with Brad Bruno, who is another faculty member in the mechanical engineering department. He worked with us on the catalytic aerogels. And Sun Through, the company that Mary and I founded, our colleagues John Costa and Adam Forty. Many students. This was from pre-pandemic, because everybody's laughing. Over 160 students have worked with us on these projects, and the Fulbright Specialist Program for bringing me here, and Professor Buratti and Francesca and Lisa for hosting me. So, and you for sitting in the audience. Okay, any questions from anyone?